result in projection theory. And I'll start by saying I probably know less than many of you about projection theory in general. But I came across a problem due to some of our opponents' work, which had connections to combinatorial geometry and incidence geometry, which is an area I know a little bit more about. And so I was excited that those ideas could help with something which on the face of it seemed like a very different type of problem, and wanted to share that with you and some of the techniques that are being used, which I think are a bit different than other techniques which have been used before in the area, and maybe these techniques will be useful for your problems as well. Okay, so I'm going to start with something which I think is fairly classical and which maybe all of you know, and this was also the start of Pablo's talk on Tuesday. So this is Marstrand's projection theorem in the plane. This is from the mid-50s. I think maybe 54 is when the paper appeared. And it says something like this. Let's say I have some set E in the plane. And maybe for what I'll talk about today, all my sets will be Borel. Maybe they can be slightly more general, but that's not really the thrust of what I want to talk about. Then what will be true, I want to consider the linear projections of E onto linear subspaces of R2. And assuming that the dimension of E isn't too big, then in general, this will preserve the dimension of E. So the dimension of E, if V is a unit vector, this will be the minimum of the dimension of E. Well, the biggest dimension this could have is 1, and this is true for almost every V in, well, I'll say V in S1. Really what I care about is almost every one-dimensional subspace of R2, and I'll just parameterize those by points on the circle. Okay, it's a 2-to-1 parameterization, not so important for what we're doing. Okay, so this is well known. And Kaufman sharpened this result slightly by trying to understand the size of the exceptional set of directions for which a statement like this might fail. And one formulation of Kaufman's result, this was, what do I want to say, 68, is the following. So let's say, again, I have some set E in the plane, but now I'm not going to consider all the directions in S1. I'll just take some collection of directions. So maybe I'll call this capital lambda. So then there exists a direction in lambda such that the dimension of E dot phi is at least as big as the minimum of the dimension of E and the dimension of lambda. And it's not too hard to see that Kaufman's result implies Marstrand's result. There have been various refinements and sharpening of Kaufman's result, and Pablo on Tuesday talked about one direction you can go with that. But I'm going to go in a slightly different direction. I'm going to look at analogs of these kinds of statements in higher dimensions, and this is also well-traveled ground. And one version of this is a result of Mattia, and I'll just state a very special case of it. This is from 75, and it's possible that this special case actually predates Mattia's 75 result, but certainly it follows from his results, even if it was already known. So now I'm going to talk about subsets of R3. And so then I want to say something similar. The dimension of the linear projection of E onto V is the minimum of the dimension of E. So I'm looking at projections onto one-dimensional subspaces, and 1 for almost every V in S2, right? So I'm parameterizing the one-dimensional subspaces of R3 by points on the unit sphere S2. And in general, if the dimension of V is not bigger than 1, then this is going to preserve dimension. Okay, so again, this is just a special case. Mattia proved in general, you can look at projections onto k-dimensional subspaces in Rn et cetera. But I'm not going to pursue it I'm not going to pursue that particular generalization. Okay, so I imagine this is known to most of you, and if any of this looks unfamiliar, it's because I've made a mistake. So hopefully, if I have, please let me know, because I know many of you are more expert in this than I am. This result of Mattia invites several follow-up questions. And one question we could ask, and I will call this question 1. What do I want to say? So I'll say, so what if, instead of taking, so when I say for almost every point in S2, I'm taking the usual surface measure on S2, or normalized, if you will. But what if I take some other measure on S2, maybe a measure which is singular with respect to surface measure? So what if mu is I'll just say singular measure on S2? Can we hope for a Mattia style result to hold? For an analog of Mattia's theorem? And that's a fairly general question because there's a large class of singular measures on S2, but we can try to narrow it down a little bit. And one way to do that is, like, maybe I'll call this question 1 prime. So I'll say, what if mu is, I say this way I'd like to say it. Well, I'll say, what is if mu is supported on a curve gamma? Okay, so this question is still somewhat general. I haven't exactly told you what I mean by a curve in S2, and well, okay, simply to be supported on a curve sounds like a slightly weak notion. Maybe we could ask, like, it's something like one-dimensional Hausdorff measure restricted to this curve, or there are various other types of measures we could try to put on such a curve. But at least this seems like a reasonable type of question to ask. And the short answer is, unless we restrict our question further, we can't hope for any sort of analog of Mattia's theorem to hold in this setting without further restrictions. And here's one reason why we can't expect something like this to hold. So here's an answer. So I'll say no. Let's imagine we have some curve gamma, which is contained in a 2-dimensional subspace of R3. So I'll say if gamma is contained in a 2-dimensional subspace of R3. So a simple example would be if gamma is just a great circle on the unit sphere, i.e., maybe I'll call this subspace V. So i.e., if gamma is a great circle, and if E is contained in the orthogonal complement of V, right? So it's either the entire line orthogonal to V or some subset of that. Well, then E, if I take any vector in gamma, take its dot product with E, I just get 0. So that's a very strong negative answer to this question 1 prime. I've given you an example of what appears to be a perfectly nice curve. And not only does a statement like this fail for almost every V in my curve, but it fails, in fact, for every single V. And so no matter what measure you're going to put on this curve gamma, you're simply out of luck. Okay, so in some sense, that's sort of the strongest possible negative answer. A slightly vague question, but one that we can try to make precise is this type of example the only way that this phenomena can fail? And one way to make that rather vague question precise is a conjecture due to Fassler and Orponen. So maybe I'll say, what will I say? So maybe, so I'll see here's a conjecture. Maybe we'll call this conjecture 1. I always butcher accents. And so they said the following, or conjectured the following. So I've just talked about some curve gamma in S2 without telling you exactly what I mean by a curve. Maybe I'll be a little more concrete now. So let's say I have some curve which can be parameterized by some C2 function from the unit interval to S2. And I'm going to ask for some kind of condition to be imposed on this curve gamma to exclude this type of counterexample. And what I'm going to require, I'll call this condition 1. I'm going to look at, so gamma of t is going to be a point on this circle. This is the C2 curve, so I can talk about the derivative of gamma of t. That'll be some vector in R3. And I can also talk about the second derivative, which will be some other vector in R3. So these are, I can think of these as 3 vectors in R3, and I want them to be linearly independent. One way to say that is I can say the span of these 3 vectors is all of R3. And I'd like this to hold for every t in 0, 1. So let's just think about this condition for just one moment. So for every t in 0, 1, this is going to be a point on the sphere. In particular, it's a vector in R3. And this is the second vector in R3. And together they span some 2-dimensional subspace of R3. And to first order, this curve is going to be trapped inside of that 2-dimensional subspace, sort of by construction. But what this is saying is the second order of that curve is leaving that subspace. So it's a very strong version of the statement that you are not trapped in a 2-dimensional subspace. You're leaving every possible subspace about as quickly as you could hope to be leaving it. So this counterexample here is very strongly being excluded. And then the conjecture is, in the sort of natural analog of Mathias's result, should hold for a curve of this type and for any sort of reasonable measure that you would put on it. In particular, there's an obvious measure just coming from Lebesgue measure on 0, 1. So let's finish the statement of the conjecture, although hopefully you could fill it in for me. So let's just write what I want to say. Let E be a subset of R3. Then the dimension of what? Well, I want to say E dot V, but I've parameterized the points of V by this curve gamma of t. So I'll say E dot gamma of t. This dimension is the minimum of the dimension of E in 1 for almost every t. In 0, 1. Okay. Maybe I'll just pause for a moment and ask, does the conjecture make sense? So it's ruled out this sort of obvious example. And I mean, I've written this for almost every t in 0, 1, but we could also say for almost every vector v on this curve gamma with pretty much any measure you want, but the obvious measure is the one coming from this parameterization. Okay, so this is the conjecture. And Fassler and Orponen proved this conjecture. Well, maybe I should give a date to this. So this was in, when was this? Thomas, help me out. 2014? Perfect. Great. They proved this conjecture in this same paper where it's stated when the dimension of E is not too big, and particularly when the dimension of E is at most 1/2. And again, we're imposing some regularity on E. We can say it's rel, for example. Okay, so I'll say they proved this. When the dimension of E is at most 1/2. And in this particular paper where they introduced this conjecture, at the time it was open for E having a dimension larger than 1/2. Then in a follow-up work, Ken Maki, make sure I spell that correctly. Orponen and Veneri, they proved this conjecture for sets E of arbitrary dimension, but for a specific curve gamma. So I'll say proved the conjecture. For gamma of t given by cosine t sine t1, and now you're going to complain that this curve is not actually on the unit sphere. So let's fix that 1/√2. Okay, so in some sense, this is a prototypical example of a C2 curve. It's in fact a smooth curve, which satisfies this condition here. And for that particular curve, they prove this result. So what I'd like to talk about a little bit today is some recent work by my co-authors, Malabika, Pramanik, and Tongou, both of which are at UBC. And the short version is we were able to prove this conjecture for general C2 curves gamma. Okay, so let's state that. In fact, we can say something a little bit stronger, which is an analog. Maybe I shouldn't have just erased it, but an analog of Kaufman's theorem. So here is our new result, just due to these co-authors I've just erased. And I'll say let gamma let's call this be a C2 curve, which satisfies condition 1. And let's say I take some set lambda, which is a subset of 0, 1. So then there exists some t in lambda such that the dimension of E dot gamma t is at least the minimum of the dimension of E and the dimension of lambda. So in particular, the dimension of E dot gamma of t is the minimum of the dimension of E in 1 for almost every t in 0, 1. Right? So this Kaufman style result implies the corresponding Mattia style result. I'll mention that this result of Kenmaki, Orponen, and Veneri, in the special case of this curve, they also prove a Kaufman flavored result, but it has a slightly different formulation than this. Nonetheless, their Kaufman flavored result is strong enough to imply the corresponding Mattia result. Okay, so I want to spend the remainder of my time describing some of the main ideas that were used in this Kenmaki, Orponen, Veneri theorem, and some of the modifications that are then needed to go from this very specific curve to general C2 curves, and also, although I haven't stated it, some changes that are needed to change their Kaufman flavored result into this Kaufman style result stated here. Okay, so I'll talk about that. Maybe just to get sort of a sense, you could ask how important is it that this curve in the Kanmaki-Orponen-Veneri theorem is of this specific form? And I'll sort of say there's roughly 3 levels of generality that one could talk about for this theorem. You could talk about this very specific curve. You could talk about C infinity curves, which satisfy this non-degeneracy condition given by equation 1. And then you could talk about curves with less regularity, potentially all the way down to C2 curves, which satisfy that condition 1. And I'll argue that each of those increasing levels of generality requires some new techniques to understand. And really the sort of the new thing is going from C infinity to C2, and that this actually requires some ideas which I haven't seen elsewhere. Okay, maybe I'll just pause and ask if there's any questions, if it's sort of clear where we are.
When you say there exists, well, that states that there is just one principle, okay, many because can always take subset. But is there any idea about the dimension of the T that are okay?
The dimension of the T that are
so the set of all T presumably is large, or I mean that's not what the statement says, but what?
Oh, sure. So okay, so there's a few different equivalent reformulations, but let's say the dimension of capital E is tau, then the dimension of the set of T for which the statement fails is at most tau. And how do we see that? Well, imagine the dimension of the set for which it fails was larger than tau, then just pick lambda to be the set of, the T which witnessed that failure. Yeah. Great. You had a question? So I would say requiring the curve to be C2 is maybe just a limitation of our method, but we need some sort of condition saying the curve can't be trapped in a 2-dimensional vector subspace, right? Because if the curve were a great circle, then you're completely out of luck. So there's different questions you could ask. You could ask that you could ask for some sort of quantitative estimate, just saying that the curve leaves any 2-dimensional subspace at a certain rate, and that makes sense even if the curve isn't C2. You could ask other things. You could, instead of asking that the curve leave at some quantitative rate, you could put some different measure on the curve, which somehow is vanishing in places where it looks like it's trapped in a 2-dimensional subspace. So there's a wide variety of questions, but somehow this is maybe the easiest and arguably the most natural one. And given that already involves some difficulties, it seemed like a good place to start. You had a question as well? Or no? Great. Okay. Let's talk a little bit about how one might prove a theorem like this. So what would I like to say? So this was an idea introduced by Kanmaki-Orponen and Veneri, which allows us to transform a problem which has this kind of formulation into a problem about curves in the plane. And this is an area where some ideas from the theory of maximal functions and other harmonic analysis tools can be brought to bear. And so what will I say? So I'll say we have some curve gamma, which is going to be fixed for the remainder of this talk. And I'll say if I have some point P in the set E, maybe I'll fix my set E as well. Did I not? Oh, I didn't, okay, maybe I should have said let a subset of R2, R3 rather, right? Otherwise, this doesn't quite make sense. So if P is in E, I'm going to define C sub P. This is going to be a plane curve, and it's going to look like T comma gamma of T dot P. Where T is in 0, 1. And what I would like to do is let's consider, maybe I'll say here I have some set E, which is in R3. And I'm going to look at the set of curves C sub P, where P is in E. And let's try just drawing these curves C sub P. So these are plane curves. Well, E is a large set, so there's uncountably many of them. So clearly I can't draw them all, but I'm just going to sort of draw a few. So I guess this is the T direction. I'll call this the Y direction. And each one of these curves, C sub P, looks something like this. So on and so forth. Right, so each one of these curves depends on the point P that I have chosen, and they also all depend on this curve gamma, which is common between all of the curves. Okay, now, why is this a good thing to do? Let's fix some value of T, and we'd like to understand the dimension of this dot product, E dot gamma of T. What you can do, so maybe I'll say here I have E dot gamma of T. And well, okay, so maybe I'll put that a little bit lower to try to draw this equivalence here. Let's pick some value of T. What I'm going to do is I'm going to draw this vertical line. Maybe I'll draw it in green. I call this L sub T. And the dimension of E dot gamma of T is equal to, in fact, they're essentially the same set as the union of these curves intersected with this vertical line, L sub T. So I have transformed this problem, which is ostensibly a projection problem in R3, into this planar problem. And I have this collection of curves. I take the union of all these curves, C sub P, as P ranges over the points of P. And I'm interested in a set of vertical slices where this union of curves has small dimension. And I'd like to show that that union of that set of values of T can't be too large. Right? So this is now the phrasing of this problem. And this rephrasing goes back to Kinmaki, Orponen, and Veneri. In their problem, because their curve was this rather special curve parameterized by cosine theta sine theta 1, these curves were somewhat straightforward to understand. They called these curves sine waves, and they're not quite circles, but they have many of the same combinatorial properties as circles, right? So a circle in the plane is parameterized by, it's described by 3 parameters. So two parameters for its center, x comma y, and 1 for its radius, r. And there's a similar thing going on here, right? Each P is a point in R3, so there's kind of C sub P is described by 3 parameters. And that's going to be a general feature. These curves come from some 3-parameter family of curves. They're not quite circles, but they have some of the same combinatorial properties and some of the same geometric properties as circles. Okay, so we'd like to show that the set of T for which this vertical slice has small dimension, that set itself has small dimension. And one way to try to do that is to discretize this problem at some small scale delta. So let's write down what that discretization might look like. Let's see how this goes. Okay, so let's try to write down a discretized version of this question that I posed to you. And so here's the kind of setup we'll be interested in. We have some small parameter, which I'll call delta. And in everything that follows, we're going to consider a single scale delta, but really we're interested in the asymptotics as delta becomes very small. And I'm going to let So I had my original set E, which was some subset of R3. We might as well assume it has dimension at most 1. In fact, just to make our life easy, we could even imagine E has dimension 1, just to be very concrete. And E sub delta is going to be some approximation or discretization of the set E at scale delta. And one way to do that is I could let E be a collection of points, each of which, or E sub delta is a set of points which are contained in E and are delta separated. And so I'm going to say E sub delta is a, okay, what's the dimension of E? Let's say the dimension of E, let's just call it tau, just some number, especially between 0 and 1 is the most interesting case. And so E sub delta is going to be what's called a delta tau 3 set. And I think, in fact, Pablo talked about these kinds of sets in his talk. But the idea is this is going to be some finite collection of points which are delta separated. We can assume everything's compact. And it's going to satisfy some sort of non-concentration condition. So if I look at a ball of radius r and I ask what fraction of all the points are contained in that ball, then it's going to be something like at most the radius to the power of tau. Okay, so you can think of this as the discretization at scale delta of a set that has dimension tau. And if you want, you can even set tau equals 1. Okay, so let's do that. I'm going to let lambda delta is a, let's call this a delta alpha 1 set. Here alpha is the dimension of lambda, right? So lambda is the subset of 0, 1 from our result. We can imagine lambda has some dimension, which I'm calling alpha. I'm going to discretize that set at scale alpha. And here's what the picture now looks like. So I do the collection of curves C sub P, where P ranges over E. Now I can look at these curves C sub P, where P ranges over E delta. So this is now a finite set of curves. But I'm considering this whole problem at scale delta, so I could thicken them by delta. And so I'm going to use this superscript delta to denote their delta neighborhood. And what does this look like? Well, now these curves have a little bit of thickness. This thickness delta, which is meant to be fairly small, but nonetheless, it is not 0. And I have this set, so this is the union of these curves C sub P delta. I have this set lambda delta. So this is a subset of 0, 1. And what does it look like? Well, lambda is a set of a certain Hausdorff dimension. So I'm going to draw some approximation of some, I don't know, half-dimensional set, something like that, at scale delta. And what is going on? I haven't drawn this picture too wonderfully, but if you were to look at these vertical stripes above each one of the delta intervals in this set lambda, what do these stripes look like? Well, first of all, they're meant to look like the discretization of a set which has a fairly small Hausdorff dimension. So these themselves are going to be like delta beta sets for some value of beta. And this is the sort of situation we're interested in trying to understand for which values of alpha, beta, and tau can this kind of picture actually happen, and for which values is it impossible. Okay, so hopefully this picture kind of makes sense. And let me just try to sort of draw one more thing, which is, so I have this, I'm interested, so for each one of these vertical stripes, I have some region where these curves live. I'll draw in red. And this doesn't look like a very good counterexample to my theorem, which is, I guess, encouraging. If I could draw a really good counterexample to the theorem, that would give you some doubts whether the theorem was true. But here's sort of my set where all the action is happening, and I'm going to call this set F. So F is the red set. Okay, so this red set is a little bit special. It's a subset of R2. Its projection to the x-axis is a delta alpha 1 set. And each of the fibers above this projection is some discretized, maybe delta alpha beta set. So sets of this form sometimes have a name, sometimes they're called quasi-products or fiber products, something like that. And we're trying to understand to what extent can all these curves concentrate on one of these quasi-product sets of this flavor. Okay, let's pause for a moment. Does this sort of make sense that maybe you believe that we have reformulated our problem, at least if you believe that this kind of discretization is possible, then what was originally a statement about the Hausdorff dimension of certain objects is now at a very concrete scale delta, sort of something that looks a little bit like a statement in incidence geometry. Okay, so I only have 10 minutes, but let's talk a little bit about some of the general ideas for how one can solve problems like this. And so as a starting point, just as a very general principle, which is used in sort of almost every problem in this area, we'd like to show that this red set can't be too small, right? If this red set was very small, that would be a counterexample to our theorem. And one way to try to understand that is, well, so what's going on? If this red set was very small, so the projection here is large, but each one of these fibers, if each one of these fibers was very small, what this would mean is that all these curves are stacking up a lot on these red regions. And if these curves are stacking up, for each one of these curves, you could consider the characteristic function of that curve. It's well defined because this thing has thickness delta. So perfectly good L1 function. It has L1 mass roughly delta. This has length roughly 1, and each one has thickness roughly delta. If these curves were stacking up a lot on these red boxes, then what this would mean is that various LP norms of the sums of the characteristic functions of these curves would have to be quite large. So in order to show that the union of these curves has fairly large volume, or equivalently that the sum of the characteristic functions has fairly large support, it suffices to show that some LP norm of this sum of characteristic functions isn't too big, right? The L1 norm is fixed. The L1 norm is just the sum of the L1 norms of all the curves, and we know exactly what that is. So for fixed L1 norm, small LP norm implies big support. Okay, so here is our new problem. Maybe I'll write this as a lemma. So here we have F is some set of this form. And what do I want to say? So let me make sure I say the exact thing I want to say. Well, okay, so maybe I'll just say, let the set of curves C sub P in E delta as above. I want to consider the sum of the characteristic functions of these delta thickened curves. So C sub P delta. And let's talk about, so we could ask what LP norm are we trying to understand? And for reasons I may not be able to get into, the 3/2 norm is the right one to consider, right? So this would be the integral as I've written it over all of R2 of this sum of characteristic functions raised to the power 3/2, take the power 2/3. But that's not quite what I want to do. I only want to consider what's going on these red boxes. And so I'm going to restrict it to the set F. And I'd like to show this isn't too large. And what we can say is that this is at most delta to the 2 minus alpha over 2 minus tau over 2 times the number of curves. And if this is a delta tau 3 set, then we should think that this has like delta to the minus tau curves in it. That's the most interesting situation. And of that interesting situation, one special case to think about, just to sort of get some intuition for what's going on, you could imagine for the moment that F is actually everything. So alpha is 1, just to get a sense of what this might say. So if alpha is 1 and tau is 1, and this is delta to the minus tau, then this right-hand side is just 1. And so we're bounding that LP norm by 1. Okay. And actually what I've written here is a slight lie. So we actually lose some epsilon. So I'm going to change this to add some squiggles in there to denote that there's some small lies going on. Okay. So what I claim is that if you can prove a LP inequality of this form, then just tracking back everything I've said so far, it will give you the main theorem. And so we reduce this theorem to a statement like this. And so far, that's not so new. I mean, these are just sort of using tried and true ideas. The real difficulty is trying to prove LP bounds for an object that looks like this. Okay, so maybe just one final remark before I move on, some interpretation of what this problem is. So in Pablo's talk, he was talking about the Furstenberg problem. And for the Furstenberg problem, you have some collection of lines in the plane, and on each one of those lines, you have some set which has a certain Hausdorff dimension, or maybe you discretize the problem, so you have some delta alpha 1 set on each one of these lines, and you're trying to understand how small can the union of all these delta alpha 1 sets be. And there's a special case of that, which he called this product Furstenberg problem, where these delta alpha 1 sets have a special form. And so this problem here looks a little bit like the Furstenberg problem, except instead of considering lines in the plane, where each one of these lines has some delta alpha 1 set on it, now we have this collection of curves. And each one of these curves has some sort of delta alpha 1 set on it. Now, these delta alpha 1 sets on each curve are a bit special because they come exactly from lifting the same subset of the x-axis to each one of the curves, right? So that's a special case of this sort of Furstenberg-like problem for circles. So that's another sort of interpretation of what we're doing here. And that shouldn't be shocking because these Furstenberg-flavored problems are closely related to projection theorems, and almost to the extent that they're kind of different formulations of the same type of phenomena, at the very least. Okay, so I have 4 minutes. Let's try to describe how we might control an object like this. And this was, again, we're just following the sort of tried and true path that Kanmaki, Orponen, and Beniri followed. And in the special case of the curve gamma that they considered, these curves, C sub p delta, have this rather special form. They, as I said, they call these things sine waves. They have many of the same geometric problems or properties as circles. And if these curves, C sub p, were genuine circles, then in the special case where alpha is 1 and tau is 1, this lemma actually was proved by Thomas Wolff in the late 90s, early 2000s, or late 90s, let's say. And this is called the Wolff circular maximum function. And he proved these sharp L3 halves bounds. And Kanmaki, Orponen, and Beniri were essentially able to transform their problem into a version of Wolff's result. Apply Wolff, not quite as a black box, but at least some of the major pieces as a black box. And then that was what they did. So then you could ask, can we do sort of this Wolff flavored result for other classes of curves? And if these curves are smooth, then in short, the answer is yes, we can apply similar ideas to Wolff to recover this result. And very roughly, well, okay, maybe I'll draw a quick picture of what this problem looks like. Let's try to understand something like this sum of characteristic functions here. And we can ask, how can this be big? And so what does it mean for something like this to be big or have big LP norm? Well, it means that these curves are stacking up a lot. And let's look at 2 typical curves. So this might be C sub P1 and C sub P2. And I have their slight thickenings, their delta thickenings. And intuitively, this LP norm is big if often these curves have large intersection. We can ask, how big is the intersection of these 2 curves? Well, if each of these curves has some thickness, if I thicken them by delta and they intersect, then in this picture, this looks like a little box of dimensions delta by delta. Seems rather good for us. And indeed, if this was the typical behavior of every intersecting pair of curves, then we'd have a much stronger result in this. We'd even have an L2 bound, which is better. The problem is that this picture here doesn't necessarily represent the typical situation. Another thing which could have happened is the 2 curves could almost coincide. So this could be the first curve, and the second curve could be very close to it. And if that happens, then the intersection of their delta neighborhoods is huge, right? It's of size roughly delta, which is as big as it could possibly be. So that seems quite scary for us. But thankfully, this situation can't happen very often because we're asking that this collection of curves be a, where did it go? A delta tau 3 set, which means once I fix my first curve, there can't be very many other curves that are very close to it in parameter space. So this kind of situation is atypical, and this is not actually our enemy. The real enemy for us is when I have two curves which are tangent. And these two curves can be quite far from each other in parameter space, but their delta neighborhoods have rather large intersection. And if this is occurring frequently, then this is genuinely a problem. So this is the kind of situation we need to think about and try to understand how often can this happen. And so this looks an awful lot like pairs of curves being genuinely tangent. And you could ask now this question purely in incidence geometry. If I have a collection of circles, or more generally a collection of curves, how often can two of them be tangent to each other? That's not quite the right question to ask because they could all be mutually tangent at a common point. So, okay, we need to rephrase this question slightly. We should ask it, how many different locations can pairs of curves be tangent? And so Wolf used some ideas from computational geometry to say if I have n curves, the number of times this situation can occur is like n to the 3/2. You track that whole thing through and you get this 3/2 down here. And with a bit of work, you can extend Wolf's techniques from circles to general smooth curves. But to do this, say for C2 curves, requires some new ideas. And I now have maybe negative 30 seconds. So I'll just maybe just write down a reference for the people who actually solved this problem, whose ideas we can now use. And they are Adam, Marcus, and Tardis. So Marcus. And they used ideas from topological graph theory, so very, very far from everything that we're doing here, to understand not just the number of tangencies between pairs of curves, but actually the number of things called lenses. So you don't have to be quite tangent, but if you're sort of almost tangent, then your delta neighborhoods still intersect in this rather large rectangle. And so they were able to show that given some fairly general collection of curves, their curves don't even have to be C2, they're just Jordan arcs. They're able to control the number of times that this picture occurs. And so if you use their result, this gives you some control over the number of regions where you have these badly intersecting curves, and you sort of unwind what they do, and it results in a theorem like this. So maybe the slightly surprising thing, which I'll just finish with, is there are several examples where we are trying to prove some sort of a discretized incidence geometry statement, and we might be inspired by results from genuine incidence geometry, so things like point line incidences or point curve incidences. But usually those sort of honest to goodness incidence geometry statements they don't immediately give us their discretized counterpart. At best they can sort of inspire the proof. But this is one of the very few, actually the only example I'm aware of, where a actual statement from discrete geometry can simply just be applied with, as a black box and say something meaningful in this discretized setting. And the reason is that in this kind of discretized setting, you still see a actual geometric, like honest to goodness geometric object, which is this thing called a lens, which is this pair of curves that are intersecting at 2 points, and that intersection is fairly localized. And so they're able to use ideas from topological graph theory to control how often that occurs, and that in turn controls how many of these boxes that look like this can happen, and that in turn gives us control on the L3 halves norm of this corresponding maximal function, which then finally gives us this projection result. Okay, so I'll finish with that.